I think today we'll have a pretty interesting lecture, and this has to deal with the temperature dependence of transport properties, in particular of metals, because they have free electrons. So first of all, let me just take a really classical view, which is a pre-quantum view for the transport properties. One transport property is the electrical conductivity. And we've already derived in the previous lecture the electrical conductivity for a sea of electrons. Conductivity is given by the number density, the charge on electron, the scattering time divided by the mass of the electron. Now this mass of the electron could be the raw mass, it could be the effective mass. We're not concerned with what this mass means, but it is some property which has dimensions of mass. So this is a classical equation, totally classical equation. Now these electrons are treated as independent particles. They are particles, classical particles like billiard balls inside a metal. The inverse of this, of course, is the resistivity, sorry. Now this 1 over tau is a scattering rate. And this scattering could be from different mechanisms. And we're going to slightly look at these mechanisms today. It could be because electrons are colliding with the electrons. It could be electrons are colliding with the ions. The ions themselves are vibrating. And it could be impurities or defects inside this metal. So all of these can contribute to the decay rate. So if you have many decay rates possible and all of those decays are independent of one another, then you can add up all the decays to give the overall decay. So if you have multiple decay rates due to multiple mechanisms, so there are n mechanisms, you can add up all their decay rates to give a combined decay rate, only when those mechanisms are independent of one another, which they rarely are. So this rule of resolving the decay rate into different mechanisms, into different channels for decay, is generally called the Matheson rule. Matheson rule. And this is something we're going to invoke in a minute. So there are different rates of decay. Each rate corresponds to a different mechanism. So this is one property which is called electrical conductivity. But there could also be a transfer of heat, of thermal energy. So if you have a solid, and there is some temperature gradient, so this is a hot end, this is a cold end of this solid, then a heat current can also flow, JQ. A thermal current can flow from the hot to the cold end. This is thermal conductivity. And this thermal current is generally given by minus kappa, which is called the thermal conductivity, and the gradient inside the temperature. So whenever there is a difference in temperature, the temperature per unit length is called the gradient, and this is a constant of proportionality called the thermal conductivity. Yes? It's a thermal current. The energy per unit area per time, so watts per meter square passing through a particular cross section of this solid per unit time. Okay, it's called thermal current. So this second quantity, kappa, is this other transport property we would like to consider. So we have an expression for the electrical conductivity. We also need a classical expression for the thermal conductivity. Now, in these electrons are now carrying thermal energy. There are different mechanisms for thermal transport inside a solid. One, electrons can carry energy. Phonons can also carry energy, but phonons don't exist in the classical model. Ionic vibrations, in other words, can transfer energy. But in solids, in metals which have a high conductivity, which means a high concentration of electrons, the electrical conductivity, the thermal conductivity due to electrons far supersedes the thermal conductivity due to phonons. So we are only considering the thermal conductivity due to electrons. Okay? So these electrons are transporting charge. These electrons are transporting thermal energy. कर सकते हैं, लेकिन उनकी thermal conductivity due to phonon is much smaller. So I do not know the physical reason for this, but the calculations indicate a much smaller thermal conductivity due to phonons. Now the reason for this, I think, is the point that the mobilities of electrons to be of the order of the speed of a Fermi electron is 1% the speed of light. It's very high Fermi speeds, which is much larger than the speed with which phonons can propagate. Okay, so the thermal conductivity for is, if we treat the problem totally classically, we can treat these electrons as a gas of molecules. So if you have a gas and there's a hot region in the gas and a cold region inside the gas, and then we look at electrons, in the hot region we will have gas molecules which are moving with much higher RMS speeds, correct? And in the cold region we'll have gas molecules with much smaller speeds, still moving thermally in random directions, but there are fewer gas molecules in the hot region but faster. There are denser concentration of gas molecules in the cold region of the gas but slower. And this is how thermal energy is transported inside a gas. So this gas will have some heat capacity, and that heat capacity is going to transfer energy from the hot to the cold end. The electrons inside this solid can also be modeled just like these gas molecules. Okay, and so they can be treated in light of the kinetic theory of gases. So in the kinetic theory of gases, the transport of thermal energy gives you a certain estimate for the thermal conductivity, which is given by 1/3, and this you can look up in any statistical physics book. I'll also put a resource on the website which will help you determine this. It's 1/3 because we have 3 dimensions. The heat capacity, CV, the RMS speed, the mean square speed of these molecules, in this case electrons, multiplied by the scattering time constant.
So ये kappa की definition.
This is kappa. So this is the classical result for thermal conductivity, and this is the classical result for electrical conductivity. So now we also know from classical physics, when we studied the heat capacity, we've already looked at the heat capacity for electrons, by the way, the Sommerfeld model, haven't we? But in the high temperature limit, which is the classical limit for the heat capacity, this heat capacity converges to a particular value, which is called the Dulong-Petit law, which is one of our lectures when we studied the free electron model. So we already know that in the classical case, CV is given by 3/2 NkB, where Kb is the Boltzmann constant, N is the carrier concentration of electrons. 1/2 Nkb is for each degree of freedom, and since you have 3 degrees of freedom because of 3-dimensional motion, the heat capacity is 3/2 Nkb. The energy is 3/2 Nkb into temperature. Heat capacity, you take the derivative of that temperature to get the heat capacity. So still in the classical model, we put this value of CV into the thermal conductivity. So all the discussion so far is focused on the classical model, and on the right side of the blackboard I'm looking at thermal conductivity due to electrons, on the left side I'm looking at the electrical conductivity. So let's insert this value of CV into the formula for thermal conductivity. Kappa equals 1/3 3/2 Nkb V square tau. Now what about V square? Can we also predict what V square is going to be in the kinetic theory of gas model? What is V square? What is the mean square velocity? Use you study statistical physics. So use the equipartition of energy. So each degree of freedom carries energy half kBt, and there are 3 degrees of freedom. So half m V square is going to be 3/2 kBt. So you pick this value of V square and insert it in here. So your kappa turns out to be 1/2 Nkb. V square is now 3 kBt over m tau. Three over 2 N kb square over m t tau. This is your classical prediction for the thermal conductivity. Got it? Now we have a classical prediction for the thermal conductivity and the electrical conductivity. Purely classical reasoning so far. What we're interested in is looking at the overall temperature dependence of conductivities, thermal as well as electrical. So see what kind of predictions does physics make about these transport properties of materials, in particular metals, because we are only focused on free electrons at the moment. So if you were to take the ratio of the thermal conductivity and the electrical conductivity, this ratio turns out to be 3/2 N kb square m t tau, and as far as sigma is concerned, we'll have m over n e square tau. Now note that I can kind of cancel out these n's, these m can go away, and I'm left with 3/2 kb over the charge on electrons square. And the next step, what I'm going to do is I'm going to take out the temperature onto the left hand side, and I'm going to form this quotient kappa over sigma t, and here I'm left with 2 taus. One is the scattering of the electrons Now, in both of these cases, there's an electron drift. There's an electron drift. Electrons are moving from one end of the solid to the other in both thermal conductivity and electrical conductivity. So both of them scatter. So these taus are cancelled out, and I'm left with simply this expression. Okay? Now this is an expression that only depends upon fundamental constants, the Boltzmann constant and the charge on an electron. Only fundamental constant, it's a fixed constant value. And this is a classical prediction for this ratio. Now this number is generally called the Lorentz number, and it's a classical prediction. Now if you look at metals and you plot this kappa over sigma t, which are experimentally determined values, because you can determine thermal conductivity and electrical conductivity, you can make measurements. Okay, so how can you measure the thermal conductivity, by the way? There's an experiment in the lab that helps you do that. No. So you can have a rod in which you apply a pulsed energy, a pulsed heating pulse, and it kind of, you have a distribution of temperatures being measured, and and from the Fourier decomposition you can find out the thermal conductivity. So this method, by the way, was invented or discovered by Angstrom in 1808. So there are different ways of measuring thermal conductivity. Nevertheless, if I were to plot this factor with respect to T, ideally one should get a straight line, right? So, which hovers at L naught. But what really happens is that at large temperatures you get a good corroboration with theory, but then it drops down at low temperatures, it drops down and then kind of goes back to its prediction. And this curve depends upon the purity of the sample as well. So here you have really pure sample, and here you have impure samples. So how do we explain this? So far we have not kind of evoked any quantum mechanics, any of the Fermi-Dirac distribution rules for electrons. There's no quantum physics in this at the moment. So now we would like to sprinkle in the Pauli exclusion principle. These electrons obey the Fermi-Dirac statistics, and there is a Fermi energy associated with all of this. So now let's add the Fermi-Dirac distribution to all of this. So for this purpose, what we really need to see is the modification in how we calculate T heat capacities. The heat capacity, the calculation of the heat capacity would change, and what other changes would be needed to these formulas. First of all, we have an expression for V. This V square. What kind of V is this? What is that V in the classical model? How much is this velocity? Which velocity is this physically in the classical model?
सारे particles हैं।
हाँ, कौन सी velocity है? Drift velocity है, Fermi velocity है, thermal velocity, कौन सी velocity है? It's the thermal velocity. In the classical model, that V square is purely the thermal velocity, because we haven't yet kind of brought in any ideas related to the Fermi-Dirac distribution. There is no Fermi velocity defined as yet. So now we would like to sprinkle in the Fermi Dirac distribution and our Sommerfeld model calculations. And you've already calculated the CV for the Sommerfeld model. So now if we make these distinctions, nothing, by the way, changes in the formula for the electrical conductivity. Okay, for the thermal conductivity, kappa, we will have 1 over 3. Now the value for CV is different from this value, and it's given by pi square n over 2 kb, the temperature, over EF, which is kbTF, right? We do know that the heat capacity is now downgraded by T over TF, right? This is something we've already derived in the Sommerfeld model. The pre-factor also changes a little bit. So we have EF in the denominator, the Fermi velocity in the denominator. So now if we would calculate L naught, when we've included FD statistics, we will have pi square over 6 n T over TF. V square is now the Fermi velocity square, right?
सर इसमें कोई टाउ का फैक्टर नहीं है क्या करना
सॉरी ये CV है, ये CV है सर, ये दिस CV लिखा हुआ है, tau. So this is L naught divided, of course, by n E square tau m. Okay. Okay. So now let's try to simplify this a little bit. This n goes away. This half mvf square is so pi square over 3 T over TF 1 over 2 mvf square tau over E square tau. Now in the numerator there's a tau and there's a tau in the denominator. Now what we would like to do is, the electrical conductivity has some mechanism for relaxation, some mechanism for resistivity, some mechanism for the scattering of electrons, and thermal transport processes have some mechanism for the scattering of electrons. So let's assign for the time being different rates to both of these processes. So one is, in the numerator we have kappa, so let's assign tau kappa to the scattering time for thermal processes and tau sigma to the scattering time for electrical processes. This half mv square is simply the Fermi energy, which is kb Tf. Correct? And isn't there an additional kb somewhere? There has to be an additional kb. Oh. So, all right. So this is actually kb square here. There's a kb here. So this turns out to be pi square over 3 T kV over epsilon square tau kappa tau sigma L naught. So the quantum prediction with the Fermi-Dirac statistics gives you a value for L naught which is essentially the same as the classical prediction. The prefactors can be different, right? So this is a prefactor, change of prefactor, but that doesn't make much of a difference. So the prefactor, barring the prefactor, if these taus are the same and these taus are temperature independent, then L naught should really be the same for the classical prediction and the prediction due to Fermi-Dirac statistics, provided these taus do not depend upon temperature. So if the mechanism for electrical conductivity and thermal conductivity, both due to electrons, is the same, the scattering processes are the same, the source of scattering is the same for electrical and thermal conductivity, then the Lorentz factor should not change as we move from classical and make the transition into the Fermi-Dirac statistics or the Fermi gas realm. You get this point? However, what we really need to see is what is the mechanism for this scattering versus this scattering. So let's talk a little bit about mechanisms for scattering. Do you get the overall gist of where this argument is developing? Okay. So now let's talk about the mechanisms for scattering. Now, first of all, I would like to propose that electrons scatter due to interactions with phonons. So there is some electron-phonon interaction that is taking place that is causing scattering. The exact mechanism of that process is debatable, or is the second order problem, but it's an electron-phonon scattering that is causing this relaxation process. Okay. Electrons can also interact with other electrons, but as I will show later in the lecture today, the possibility of electron-electron scattering is really minute and shows up only at very small temperatures. So what is the mechanism for scattering? In other words, are these two scattering rates the same or different? So we really need to see how this scattering process unfolds. So if an electron is interacting with a phonon at high temperatures, okay, questions. What would this rate depend upon? Electron-phonon scattering has a certain rate. What would this rate be really dependent upon? Temperature. So let's build this argument. The temperature goes up, what happens? Which velocity? Thermal, we're not talking, so electrical conductivity has nothing to do with thermal velocity at the moment, very little to do with thermal velocity. The drift velocity is all that matters. So how does increasing the temperature have an impact on the scattering rate? Now think quantum mechanically. So there is a particle called an electron and a quasi-particle called a phonon inside the system. So what happens when the temperature, for example, increases? What happens to the number of phonons? So the phonon is a scatterer. Let's kind of write down this argument. The phonon is a scatterer. Okay? So as the temperature goes up, what happens to this scatterer, to the number density of these scatterers? Does it increase? Yeah, it does increase. So the number of phonons in the system increases, right? So if I were to find out the number of phonons in the system, n, number of phonons, higher the number of phonons in the system, higher would be the scattering rate, correct? Higher the scattering rate, smaller the thermal conductivity, smaller the electrical conductivity. And if both of these, suppose they have a temperature dependence because there's a number of phonons dependence, if both of these rates go equally down, or they work together in tandem, which means the number of phonons goes up, both of these go equally down, they have the same dependence on the number of phonons, then the Lorentz number will be independent of temperature. Okay, so this is something we're trying to investigate at the moment. So how do we calculate the number of phonons in the system? From your basic Sommerfeld expansions, what is the number of phonons? If I want to write an integral for this, what would that be? Fermi-Dirac distribution, right? So let's put omega here, okay? I can specify in terms of energy or omega, the density of states, g omega, which for phonons, let's look at the Debye model. Let's assume we are working with the Debye model, there is a dispersionless relationship for the acoustic phonons. So in the Debye model, we know that this is proportional to omega square, which is g omega, with some pi square speed of sound cube. Let me write down the exact coefficient for this. Pi square b cube. The volume of the solid, but the volume of the solid, since we're talking about the number density, so we divide by the volume. So this is the number density of phonons. Number density of phonons, pi square v cube d omega, right? So this is the total number of phonons. So this term here is the density of states, the specific density of state, because I'm dividing by the total volume, I get the per volume density of states, g omega. This is the Fermi-Dirac distribution for the electrons. And what are the limits here? 0 to, in the Debye model, what should be the upper limit? So in terms of omega, this is called omega d, the Debye velocity. Okay? So this turns out to be 1 over pi square v cube, this small v is the speed of sound, d omega, omega square 1 over e h bar omega kbt minus 1. So this is the number density of phonons. I can plot this number density, of course, depends upon the temperature. Correct? So more phonons, higher will be the scattering rate, smaller will be those taus. Higher scattering rate means the smaller relaxation time, a smaller tau. Got it? So this is the number of phonons inside the system. So I can also plot this. You can do a substitution. You can replace h bar omega kbt by x and do this calculation. You can find out what this integral looks like. So then this has to be written in terms of energy as well. You can also, but this will generally it's written in terms of omega, because what will be the energy then? You will have to find out the energy corresponding to omega d, which will be h bar omega d. This is not the Fermi velocity, this is the Debye velocity. This is not, so we are using the Debye model at the moment. So you can use either, but here I am looking at the Debye model. Okay? So by the way, what is omega d? How can I find omega d? What's your best bet of finding omega d? The Debye frequency for a solid. the number of modes inside the system, the total number of modes
Degrees of freedom.
is, let's suppose we have three-dimensional system, number of unit cells is C, and we have say R atoms inside a unit cell. This is the total number of degrees of freedom inside the system. This must equal 0, omega d is the range of integration, and here write g omega, which is 1 over pi square v cube omega d d omega omega square. This will immediately give you omega d, right? Omega. So this is how you find out omega d. So this omega d is known by looking at the size of the system, correct? So omega d is known. So now you can use these expressions and put this value of omega d that emanates from this calculation into the upper limit of the integration and find out the total number of phonons in the system. What is your prediction? As temperature goes up, what happens to the number of phonons? It must go up. And I'll show you what the graph looks like in a minute. So another, so higher the number of phonons, but all of those phonons will not have the same energy. Those phonons will have different energies. So what you could also do is, you could, if I look at this expression g omega f d omega, which is 1 over pi square v cube omega square 1 over e h bar omega kbt minus 1. What does this expression physically correspond to? What is this number? Physically, what is the meaning of this? So that's just the integrand in this integral. What is this? Then what does this correspond to? Number of phonons in what range? Between omega plus d omega. So it's a number of phonons inside this range. So it's like a probability distribution of phonons. It's a distribution of phonons. So let's call this p omega. So it's a probability distribution of phonons. So now what I could do, I could plot the number of phonons with respect to temperature, and I could plot the number of this probability density of phonons with respect to omega and see what these graphs look like. Okay, so let me show you the plots for this. At the moment, our interest is looking at the density of phonons, because the density of phonons is important in determining what the scattering rates are going to be. Correct? So it's a long drawn out argument, but nevertheless it's important to give you a feel of how these calculations work. So let's try to plot these. You see this plot. On the x-axis I have the rescaled temperature. It's the temperature as a function of the Debye temperature. So it's a rescaled temperature, dimensionless temperature, and here I have the number of phonons. So it's largely linear. In this range, it's largely linear for temperatures close to room temperature or temperatures that we're generally accustomed to. Only at very low temperatures, the number density of phonons, as we all know, has a T cube dependence, a cubic dependence on the temperature. So there's a low temperature regime and a high temperature regime. So this is how the number of phonons inside that overall solid depend upon the temperature of that solid, the ambient temperature of the solid. So higher the temperature, you would expect more scattering. The thermal conductivity should technically drop, and the electrical conductivity should technically drop, which it does, by the way. But the thermal conductivity gives you a totally different behavior. So we're going to investigate this. So this gives you a good semblance of how the number of phonons in the system vary with temperature. Now in the second curve, in these curves, what I've done is I once again redefined everything in dimensionless terms. So I define F, this F here, is the ratio of omega. It's a rescaled omega. It's omega, the ratio of omega with the Debye frequency, omega over omega d. And this R is the temperature, rescaled temperature, temperature divided by the Debye temperature. So I'm kind of rescaling everything in terms of the Debye upper limit, which is the cutoff frequency and the cutoff temperature. Okay, just to make the plots easier, because I don't want to use numerical values of AH and pi and speed of sound, right? So I'm making everything dimensionless as is commonly done. It gives you a good understanding. So when I plot this curve, this is what it looks like. Now this is a plot of the probability distribution of phonons, P, that I wrote on the blackboard. So on this axis, I have frequency, omega. When omega is 1, this is the Debye frequency, the upper limit. That's the maximum frequency of any phonon that can exist inside the solid. You cannot have a frequency higher than this in the Debye model. Why? Because if you have a frequency higher than this, then it means that the wave has a wavelength shorter than the interatomic spacing. And that is where the Debye limit breaks down, because the Debye model assumes that everything is a continuum, right? It does not take into account the graininess of matter. Everything is an elastic continuum. So this is the maximum frequency of any phonon that exists in the solid. Omega equals omega d here. And as the frequency increases, you can see these humps. And these different graphs correspond to different temperatures. This 0.1 is the lowest temperature. The temperature here is 0.1, which means 10% of the Debye temperature. This is 20% of the Debye temperature. And here I have 30% of the Debye temperature. Now there is a hump. And if I were to take the location where this probability distribution is maximum and look at that frequency, h bar omega, and find that frequency and find the temperature corresponding to that frequency, then that temperature will be equal to T, the temperature at which this curve is drawn, which means that the maximum probability distribution, the highest number of phonons, there is a mode in the probability distribution for phonons which energy kBt. So kBt, so if you have, in other words, in simple English, if you have a solid at temperature T, the typical energy of a phonon is kBt. So you take this curve, find its derivative, and see where that derivative is, find the frequency corresponding to that derivative, find out the temperature corresponding to that frequency. It will simply be T. So kBt is the expectation value for the energy of a phonon. Most phonons will be centered around this energy kBt. So if you have a solid at temperature, the highest likelihood to find a phonon at a particular temperature, at a particular energy, will be kBt. So most phonons will have temperature kBt. Okay? And the number of phonons is also going up, as you can see from these humps. If, however, the temperature is really large, so here I have plotted with respect to 50% of the Debye temperature, and here is at the Debye temperature. This curve starts looking like this. Okay, so now what do we learn from these graphs? The first thing we learn is that the number of phonons increases with temperature. The second is that the typical energy of a phonon at temperature T in a solid is kBT. Okay, so let's write down these two dictums. Temperature, number of phonons, this kind of has some non-linear dependence here, and then it goes up like this, right? Higher the temperature, higher will be the number of phonons inside the system. The second graph that I've drawn is with respect to omega over omega d, the probability distribution function p omega, and these graphs look like this. And at this maximum, you take the derivative of dp omega with respect to omega, put this equal to 0, find this omega max over omega d. This omega max over omega d, you then find this omega max, so h bar omega max will be equal to kb, the temperature of this solid. Okay, so these are the two relationships that we've figured out. So most phonons in the system are at the temperature kBT inside this solid. Now how does scattering take place? Let's see. If I were to ask you, I don't want to do this calculation right now, but if I were to ask you, can you prove this number of phonons is proportional to T at high temperatures, which means when kBT, when T is much larger than the Debye temperature. Can you prove this? Of course I can. If I take this integral, at large temperatures, this becomes a small number. So this becomes 1 plus h bar omega kBT, 1 minus 1, this T goes into the numerator. Correct? So at large temperatures, the number of phonons is proportional to the temperature. And it's also evident from this graph, right? So it's a linear relationship with the temperature. And at small temperatures, this number of phonons is proportional to T cube. This is something you can also prove, right? So this should be homework problem. कर लेना खुदा के लिए इसको. देखो मैं कोशिश कर रहा. I know that it's a dense material. It's kind of things are connected together, but I'm trying to do it very systematically. But let's hope I kind of partially succeed in this. So now there is a temperature dependence on the number of phonons, and this has a direct bearing on the scattering rates, because now there are different dependencies of the number of phonons on the temperature. So tau immediately is temperature dependent. When tau is temperature dependent and the temperature dependence changes for thermal and electrical conductivity, it's dissimilar for tau k and tau sigma, then this L will not be the same as L naught at all temperatures, and you can expect to see a behavior of this kind. So now how does scattering take place between electrons and phonons? First of all, let's look at electrical conductivity. If I were to apply an electric field on a sea of electrons, its momentum is going to change. And the change in momentum, let's say h bar delta k is the change in momentum of the electrons, and each electron has a k value. H bar k is the force, which is minus EA. This is the force, right? And delta k is a change in wave number. So the change in momentum is a force into time, isn't it? So tau, sigma. So change in momentum, this is Newton's law, change in momentum. Momentum is for each electron is h bar k. The change in momentum is force. What's the force? Force is electric field into E, into the scattering time. So an electron is moving with a certain speed before it is scattered. So for a time tau, it moves under the direction of that electric field, under the action of an electric field. So on average, all the electrons in the presence of electric field get a kick in the momentum. Alright? Their k value goes up. So now if I were to plot suppose this is my k, and I plot the Fermi-Dirac distribution function as a function of k. So instead of energy, I am plotting the Fermi-Dirac distribution as a function of k. And I am at finite temperatures. T is greater than 0. So suppose I just plot with respect to one axis kx, and the electric field is also applied along the x-axis. So in the absence of an electric field, what will be the Fermi-Dirac distribution look like? Of course it's going to look like, so since it's a momentum which will be positive or negative, electrons can be moving to the left or to the right, so they will have x components of their k vectors to the left or the right. And of course everything is quantized as well. But if you plot the Fermi-Dirac distribution function, there is an upper limit of kx, which is at the edge of the Brillouin zone. This is at the Fermi energy, at the Fermi wave vector. So, and since it's at finite temperature, so you'll get a kind of smearing out of this Fermi-Dirac distribution function like this. Likewise for the other direction. Okay. So this is the Fermi-Dirac distribution in the absence of an electric field. Now I do apply an electric field along this negative x direction. This is the direction of the electric field that I apply. What happens to this Fermi-Dirac distribution function according to this formula? The momentum, right, the momentum of each and every electron in the system gets a positive kick in the kx direction. So everything starts to move along the x direction. So the increase in momentum corresponds to the drift velocity, not the thermal velocity but the drift velocity. And remember that all the states inside this distribution curve they're populated. There are no vacant states here. Now everything in the presence of electric field, now you have a proper quantum mechanical picture of how conduction takes place. This entire Fermi-Dirac distribution function gets a tiny shift towards the right, which means there are more electrons moving in the plus kx direction than in the minus kx direction. And that corresponds to the drift of that giant sea of electrons in the positive x direction. So this distribution function kind of slightly shifts. Like this. So there will be an excess of, this will be the excess of electrons that have a positive kx, which corresponds to conduction, electrical conduction. Correct? Now this shift, by the way, delta Kx, this is Kf here, is much smaller than Kf. And I'm going to give you a homework problem on calculating how much small. It could be 5 orders of magnitude smaller, because Kf is very large. The Fermi velocities are very large, and the shifts and the drift velocities are very small. The Fermi velocity is, say, 1% the speed of light, and the drift velocity is a few millimeters per second. So it's going to 6-7 orders of magnitude difference. So this shift is absolutely small. I mean, this kind of overpopulation, this net population difference of plus kx electrons is really small. It's a small fraction of the overall number of electrons. And even this small shift is sufficient to give us electricity, to give us conduction. Now, if I were to draw a picture, a really nice picture of this, and draw it in the kind of a Fermi circle. Now, this is my Fermi sphere. Now, at finite temperatures, there is an equal smearing. So all of this is, of course, filled, right? This is all filled. This is Kx and this is Ky. Now at finite temperature, of course, there is some spillover. There's some spillover across the edge, right? Equally in both directions. Right? Some electrons have kind of overspilled in outside the Fermi sphere, right? Because there's not a sharp precipice here. This Fermi Dirac distribution curve has kind of gone beyond the Fermi level because of the finite temperature. This, by the way, how much it goes out is of the order of kBt, the typical energy of phonons. Now, when you apply an electric field in the negative x direction, there is a net drift of electrons in this direction. So what happens in that case is that this entire Fermi sphere shifts slightly in the direction of positive kx. And as a result of this, there will be more spillover in this direction, and since these electrons have kind of moved away, this region will now be devoid of filled states. It will have vacant states, which I am representing by these open circles. There will be some open circles here because electrons have been depleted from this region, correct? And there are some filled states here, and most of the states here are filled. There will be some vacant states here. So if I redraw this diagram, let me redraw this diagram to make the filled states. I'm calling the filled states just electrons, and the vacant states I'm calling holes. Okay? So if I redraw this diagram in some more detail, in the presence of an electric field in the negative x direction, I'm going to have more filled states here, which are these filled circles. Filled states. right? And here I'm going to have some holes on this side. Holes. This is starting to look like an embryo. But this is what the picture is. All right, now what's going to happen? So the entire Fermi sphere has shifted towards the right. Now, how does scattering take place? If scattering really means that an electron's drift in the x direction, its momentum in the x direction, its kx is impeded, which means that the electron cannot move further. So this process of relaxation is causing scattering. Okay, so now what we would like to see is first of all, let's see how scattering would take place. Scattering would take place by an electron trying to fill a hole. So how would that happen? That would happen if, remember, this is a momentum axis, kx. How would that happen? That would happen by this electron. Now the electron cannot go inside the Fermi sphere because everything is already filled. That's the Pauli exclusion principle. The electron must go into a vacant state. And it must be in the direction opposite to kx because it's a scattering process. Otherwise, the kx will keep on increasing indefinitely and the conductivity will be infinite. That's not possible. So what a scattering event, which is happening ultimately due to a phonon, is what that in effect does. It kind of makes electron transition into a hole, go into an empty state. Now there are empty states on the further end of this Fermi sphere towards the negative x direction. So the most effective way for electrical resistivity then is that an electron fills a hole, drops off into a hole. This transition takes place. These kinds of transitions which back project the electrons, they give a negative kick to the momentum of the electrons so that the electron falls into a hole. If there is a phonon of sufficient energy available, that can produce this back kick, we're good. Okay, so this is how this electrical resistivity or electrical relaxation takes place. Now these are momentum reversing kicks to the electron that are needed, and phonons must provide sufficient energy so that this momentum reversing kick can take place. Let's see how this is affected by phonons. Yes, please.
Sir, you're saying if phonons energy provided to allow the electrons to move inside the Fermi sphere?
They never go inside the Fermi sphere. They have to go outside the Fermi sphere because everything inside the Fermi sphere is mostly filled up. So what happens? How does relaxation happen? It's a dynamical process. So when this situation is achieved, the electric field is still on. There's going to be relaxation if allowed. And then since there is still an electric field, an equilibrium state is achieved, which is of this kind. Okay, but scattering ultimately depends upon this back momentum kicks. This is called, by the way, a horizontal process. So now, how is this taking place? First of all, there could be elastic collisions and inelastic collisions between electrons and phonons. So let's look at inelastic collisions. अभी बाहर तो नहीं ना आई दुनिया, लेकिन वक्त भी नहीं हुआ अभी तो. Okay, so if you have an electron of momentum k1. It can absorb a phonon of some momentum q and get, so this electron then gets a new momentum k2 and a new energy. So phonon absorption can take place in this manner, in which the wavy arrow shows a phonon. So energy and momentum conservation dictate that k1 equals k2 minus q for this process, for this absorption process. Correct? And energy E1 plus EQ, sorry, E1 plus EQ is E2, where EQ is the energy of a phonon, which we know at room temperature is of the order of h bar omega, kBT. So this condition has to be satisfied for absorption of a phonon, and this is a kind of a Feynman diagram. But the phonon, the electron can also emit a phonon. So for this absorption to take place, there should be sufficient number of phonons available so that the electron can take up a new, and there should be some place for the electron to go to, some empty k level for the electron to go to. So everything has to be kind of constrained, everything is constrained. The second process for emission of a phonon is that the electron comes in, some energy, it produces a phonon, generates a phonon of momentum q, and this electron then goes away, walks away with another momentum k2. So in this case, k1 equals k2 plus q, and E1 minus EQ equals E2. So for absorption this must be satisfied, and for emission this conservation law must be satisfied. Okay, right. So if we now, any questions? Temperature T, the phonons that are available are at energy kBT. So this energy here is of the order of kBT. So this is clear for absorption. For emission, it might appear, okay, this is a very important point, or it's a subtle point, so I'll going to speak slowly. For absorption of phonons, the phonons we know have energy kBT. For emission, it might appear that the electron can give out a photon of any energy less than its own energy. But that's not possible, because after the emission of a phonon, an electron must keep on living, which means it must go into a vacant state. And vacant states are only available near the edges of the Fermi sphere. And the vacant states are only available, so this is the Fermi sphere, the vacant states will only be available in a thin band around this Fermi sphere. The length of this band is about kBT. That's the smearing of the Fermi Dirac function. So if a phonon, so therefore an electron can only emit a phonon of energy kBT. So that the electron after the emission of this phonon has somewhere to go to. It can see a vacant parking slot, so that it parks at a vacancy. So the emission and absorption of phonons only takes place when the phonon has energy kBT. Everything is fine-tuned at this kind of narrow range, both absorption and emission. So that's a very subtle point. So now let's look at, so once we've seen how this electrical conductivity pans about, and we'll talk about the scattering times in a minute, we know what kind of process is needed for electrical resistivity. It's a momentum reversing kick, right? So really, if I look at the Fermi sphere, if there is an initial momentum of electron k1, it must go to the opposite side of the Fermi sphere. So it must have get a new momentum k2. So, and because of the conservation of momentum, this process must entail a change in momentum q, which is provided by a phonon. So if this process is possible, then electrical conductivity, electrical resistivity or scattering takes place. Now if you have temperature T, so this T now kind of can be large or small. It depends upon what temperature we're talking about. And I'll talk about the scattering times in the next lecture, but this is the kind of transition that is needed for scattering in the electrical sense. Now let's talk a little bit about thermal conductivity, and we'll continue our discussion. We'll take 5 more minutes and then we'll continue our discussion in the next class. So about thermal conductivity, so let me draw the curve in the presence of at uniform temperature. At uniform temperature, this is Kx. Right? Now suppose we are solid, is our pictogram of our solid, this is the x-axis, and we make the left end hot and the right end cold. What do you predict would be, so this is Kx. Electrons are now moving from the hot to the cold end. They are transferring energy from the hot to the cold end. The electrons are not physically moving, it's the kind of, I drew a diagram, they're behaving similar to gas molecules. But the electrons, the energy is transporting from the hot to the cold end. How will this curve change? पूरा का पूरा. So there will be more, there's going to be, so what's going to happen to the electrons is that this edge, the positive Kx edge, will be more smeared out as compared to the right edge, because electrons in general will tend to have a higher value of Kx. So this curve kind of will smear out in this direction or in this fashion. There will be smearing effect here in the direction of positive Kx. So this yellow curve is for a temperature gradient. There is a temperature gradient. And on this side, this will become steeper. There will be an anti-smearing effect. So the electrons will not slip away or leak out into positive Kx's. They want to tighten this distribution curve will be tightened on the cold side, on the hot side, sorry, on the hot side, which hot side really means that negative Kx, on the negative Kx side, this distribution curve will be tightened. So there will be an anti-smearing effect here. Okay, so the behavior of the Fermi-Dirac distribution under electrical fields and thermal gradients is totally different. So now let's make the equivalent diagram to that diagram that we've drawn over there. In the presence of a thermal gradient. So in the presence of a thermal gradient, as you can imagine, electrons, this is the positive kx side, electrons will slip away. Still, this band is not going to extend far beyond kBt. It's still remains of the order of kBt. And there will be holes now created over here.
Inside or outside?
Inside the sphere. Outside there will be electrons. They will be smearing out. The electrons will go outside the sphere. This solid line represents the original solid when there is no temperature gradient and it has uniform temperature. Now there will be more electrons slipping out onto the positive kx side, and there will be holes created here. And electrons, so this will be filled electrons over here. Now let's see how thermal relaxation takes place. So one mechanism remains the horizontal process. This electron can take up this transition, but it's far easier for electrons to kind of fall directly into the holes that are nearby, because this requires smaller amount of energy change, right? So instead of these horizontal processes, these so-called vertical processes also take place. Which happens easier? Which is easier? This process is much easier. So the tau for thermal processes is much smaller than, can be smaller than the tau for the conductive processes. Right? Which means that the Lorentz factor can be smaller than the optimal nominal Lorentz factor that we've derived. So it's far easier for the electrons to make this vertical transition remaining at the edge of the Fermi sphere. Okay, phonons are available, and this transition is also available. So that's why we can explain this kind of relationship, that partially, at least qualitatively, that L can be below the nominal value of L naught, because now if you look at the formula over here, this tau kappa can be smaller than tau sigma. So this can be less than the nominal value of L naught. Now in the next lecture, what I would like to do is kind of describe two graphs. One is, if I take the temperature and plot the resistivity, I get a graph which is proportional to T at high temperature regime. In the middle regime, it can be proportional to the 5th power of T, and at some low value of T, it just goes down to some intrinsic value which depends upon the number of impurities. How do we explain this graph? Exactly with the same reasoning we are able to explain this graph. The second thing I would like to show in the next class is that if I have temperature here and I plot the conductivity, at large temperatures, the thermal conductivity actually plateaus off to a constant value, and then it goes up, like with a 1 over tau square dependence, and then it falls back. So how do we explain these graphs? Exactly using the same reasoning that we've kind of invoked today, we'll be able to tell how the resistivity and the thermoconductivity of any free electron based metal can be described. So thank you very much. See you Wednesday tomorrow, 5 p.m.